Hey guys, I wanted to do a couple examples with you if you don't have something that has uniform mass density. So this shows up once in a while. If it doesn't have uniform mass density, they'll give you a function for what the mass density is. So we identify the linear mass density as lambda, and this is going to be the relationship between our mass per unit length. So this is a lowercase lambda. If we think about this as being the whole mass and the length, we can think of a little tiny sliver of whatever this rod is as being a real small amount of mass that would have a width of dx and a mass of dm. So I can think of this as being lambda is going to be our tiny little change in mass over our tiny little change in distance. So if they give us what our function is for lambda, we'll be able to plug it into the integral off of the equation sheet. I've seen this show up a couple times in free responses. I'll show you an example on that. I've also seen it show up a couple times on multiple choice where they give you the lambda. So we're going to do an example with a rod. I know that on our equation sheet, that the integral for the moment of inertia is given as the integral of r squared dm, which is problematic because we have one variable and a change in a different one, and we have to substitute in. And we've already gone over how to do it for a rod that is uniform mass at different lengths, and they often will ask you to do that as well, so you can figure out what the moment of inertia is at any given point on said rod. Because this is going to be a rod, I'm going to substitute out my r for an x. And so I'm going to say that I is going to be the integral of x squared dm. And I'm saying that this is just going to be a distance. I know for a lot of them, we were dealing with a disc or a hoop. We've done those derivations. But if they're going to give you one that is nonlinear, they want to see that you can do the calculus, but they don't want to give you something that's going to take a bunch of time where you're just doing calculus for most of it, because they also want you to be doing physics. And so they often focus on a non-linear rod, or we'll see one of the examples where they had a triangle that were like spokes in a wheel. All right, so our first example, we have the rotational inertia of a rod with a non-uniform mass density about its edge. So I want to know what about its edge will be there. So I'm going to take this to be 0, and I'm going to take this to be L. Why am I going to take this to be L? Because all of our moments of inertia that we saw for rods, whether it was about the end, the 1/3 ml squared, or about the center, the 1/12 ml squared, or the ones that we used the parallel axis theorem to move, always had L for the length. And they're going to tell us that it is a non-uniform mass density, and they're going to give us what lambda is. So I know that lambda is going to be this change in mass over this change in distance. If I think about a tiny little sliver, and I'm going to say that it has a width of dx and it has a mass in there of dm. So I'm going to start with what we have on the equation sheet. We're going to say that on the equation sheet we have the integral of r squared dm. I'm going to substitute out r for x because that's what they're going to give us the function as. And so I have that I have the integral of x dm. And now I'm going to get rid of dm in terms of dx. The connector between the two of these is lambda. So dm is going to be lambda dx. And then I can plug in what our value is for the function. They're saying that lambda is cx squared. And they often use like A, B, and C. You've seen this on the multiple choice and the free response, right? They'll give you what the variables are, and then they'll give you a number to plug it in, which is a little bit different. So I'm going to have cx squared dx is dm, and this is going to go into here. So I am going to integrate. I'm going to take the c out because that's a constant from 0 to L, because we're saying from the end of the axis to the edge of our rod. And I'm going to have x squared times x squared dx. So I can combine these to x to the fourth power dx, and then this is simply going to be x to the fifth over 5 from 0 to L. And I'm going to have c times L to the fifth over 5 minus 0 to the fifth over 5. And so I get that this is c over 5 L to the fifth. All right, so let's look at an example from the AP test, and they're going to include all sorts of other skills, which are good for us to review, but the one part of it is we have this non-uniform density that they're going to give us. There isn't a bunch of room on where the problem is, but if you do it on the back of this page, I made these single-sided, so that'll give you a little bit more room to operate, to put down your solutions. All right, so this was 2018. This was the third one. The way that it normally works, you're going to have a problem where you're going to solve in variables. You're going to have a problem where you're going to solve in numbers. And you're going to have a lab one where they're probably going to make you organize data, graph it, and use the slope for something. In one of those three, there's going to be one where you have calculus. Either you will integrate, or they'll just make you write down what the integral is because they don't want to take up all of the space. So in this case, I have a triangular rod, something different. It has a length of L and a mass of M, and it is a non-uniform linear mass density that's given by lambda equals 2m over L squared x, where x is the distance from one end of the rod. Using integral calculus, show that the rotational inertia of the rod about its left end is ml squared over 2. So we're just going to get the moment of inertia for one of these, and you can see down here, they're going to make it so that we're going to have a hoop by itself, and then each one of these is going to be a spoke. All right, so I have what lambda is equal to. It is going to be this 2m over L squared times x. And I know that lambda is also going to be our small change in mass over our small change in distance as this goes. And so I can move this around and get that the change in mass is going to be equal to this lambda times dx. And so my small change in mass is going to be 2m over L squared x dx. A lot of letters. And we need to figure out which ones are changing and which ones aren't. So it turns out in this formula that the m and the L squared aren't changing. So again, I'm going to start with my moment of inertia, which is going to be r squared dm. I'm going to put in x squared for this, and then I'm going to substitute in this for dm. But the 2m over L squared, I can put that outside the integral, right? It makes it a little bit easier because it's going to be a constant. So I'm going to have 2m over L squared, the integral of x dx times x squared. So I have x squared x dx, and we're going to go from 0 to L because they're telling us that the one end of the spoke or the triangle is 0, the other end of the triangle is L. So I can combine that x squared and x to an x cubed, and I have that 2m over L squared from 0 to L of x cubed dx. So this is going to be 2ml squared. I have x to the 4th over 4, and this is going to go from 0 to L. And so we're going to have L to the 4th over 4 minus 0 to the 4th over 4. So it's just going to be L to the 4th over 4. So this is going to be, I'll write it right here, 2m L squared, L to the 4th over 4. And we can see that an L squared will cancel out in the bottom and leave an L squared in the top, and we can cancel out a 2, and I end up with 1/2 ml squared. And so what they want to see you be able to do is do the integral. They're not going to give you super hard integrals, and that's why very often it's a rod. Because once we start talking about areas and volumes, it's way more calculus than physics. All right, so each one of these has this 1/2 ml squared, and I have 5 of them that are going to make up my spoke, and I also have this hoop. So the thin hoop shown above in figure 1 has a mass of m and a radius L and a rotational inertia around its center of ml squared. 3 rods identical to the rod from part 1 are now fastened to the thin hoop as shown in figure 2 above. Derive an expression for the I total of the hoop rod system about the center of the hoop. Okay, so I total is going to be equal to the I hoop plus 3 times the I of the rod or the spoke or whatever you want to call this. So they're telling us that the hoop is ml squared, and then we solved that this was 1/2 ml squared. So I'm going to have 3/2 plus 2/2 ml squared, which is going to be 5/2 ml squared. All right, the hoop rods system is initially at rest and held in place, but is free to rotate around its center. A constant force F is exerted tangent to the hoop for a time t. All right, so if it's tangent to the hoop, then my R is going to be equal to L. Derive an expression for the final angular speed of the hoop rod system. Express your answers in terms of ml, F, delta t, and physical constants as appropriate. All right, so I know that my torque times time is equal to my change in momentum. That's a great equation to know. It's also good to know that the torque times our angle is going to be equal to our change in kinetic energy or our work. because they'll have you compare these two and contrast them. All right, so on this side, torque is R cross F. If it's acting tangent, it's just going to be R times F, because remember, the cross product just combines the perpendicular components. So this is going to be L times F times delta T. It's starting at rest, so my initial angular velocity is going to be 0, and so this is going to be my moment of inertia times my final speed, omega. Because we're saying that omega naught is 0, so that would mean angular momentum naught would also be 0. All right, so I can't use I. I'm going to have to substitute in my 5/2 ml squared for my I. So why don't I do that? When I divide I to the other side, I'm going to have L times F delta T over 5/2 ml squared. And I can simplify this or I can not simplify this. Doesn't really make a difference. We can get rid of one L. I could take the 5/2 and flip it over and make it 2 fifths. All right, let's see what else they're having us do in this problem. And although it's not going to be calculus things, it is good review for the exam. All right, the hoops rod system is rolling without slipping along a level horizontal surface with an angular speed omega found in part C at time t equals 0. The system begins rolling without slipping up a ramp as shown in the figure above. So maybe I should simplify this because I feel like I'm going to have to use it. All right, so I'm going to cancel out an L, and I'm going to end up with 2 fifths F delta T over ML. And again, if you're doing variables, you want to make sure that you are being case sensitive. So if they have a capital M for mass, then you want it to be a capital M. On the figure of the hoops rod system below, draw and label the forces, not components, that act on the system. Each force must be represented by the distinct arrow starting at and pointing away from the point at which the force is exerted. So it would have a force of gravity that would be capital M, G, that would be acting at the center. It would have a frictional force that would be acting at the point of contact along the direction of the incline, and it would have a normal force that would be acting perpendicular like that, and they kind of cross. Justify the choices for the direction of each forces drawn in part D. So mg is going to act at the center of mass, which will be the center of the hoop. N acts perpendicular from a surface. Friction is providing the torque that is turning our hoop. So it's turning it this way, which would be counterclockwise. So it must be acting parallel up the incline. All right, derive an expression for the change in height of the center of hoop from the moment it reaches the bottom of the ramp until the moment it reaches its maximum height. Express your answers in terms of ML, I total, omega, and physical constants as appropriate. Okay, so I have a conservation of energy problem. So I'm going to say that as I reach the bottom, I am going to have two types of kinetic energy. And I'm going to take that bottom of that ramp. I get to choose what height is 0, and I'm going to take that to be the height of 0. And really, I'm taking the height of the center of mass to be 0 because I'm interested in how high the center of mass goes up. But it's going to be the same if we're taking it from the bottom to the bottom. When I'm all the way up, I'm going to have potential energy of position, which is going to be delta UG. All right, so my kinetic energy is going to be 1/2 big M V squared. My rotational kinetic energy is going to be 1/2 I total omega squared. My potential energy of position is going to be big M G H. So what's in my equation I'm not allowed to have? V. I'm not allowed to have V in here. So I need to get rid of it. But I have a relationship between omega and V. So in non-slipping situations, I know that V is going to be equal to omega times R if it's not slipping. All right, so I'm going to substitute that in for V, and I'm going to get 1/2 M. I have omega times R squared plus 1/2 I total omega squared equals MGH. And I have another thing in here that I'm not allowed to have, and I can't have R. I have to have L. So I should have substituted this in as omega L. I'll do that right now. So you have to be careful. I'd always check at the end if you're doing it in terms of variables, you don't have the wrong variables. So I'm going to have 1/2. I can actually factor the 1/2 out. I'm going to have M omega squared L squared plus I total. Actually, I can factor out an omega squared, right? So I'm going to have 2 omega squareds. So I can factor out a 1/2 omega squared M squared L squared plus I total is going to be equal to MGH. So H would be equal to this divided by MG. And again, you don't want to put in the value for G. They want you just to leave it as such. All right, so I think that does it for that one. And you might see this on a multiple choice or free response.